Residual plots. What is a residual plot? It is a graph in which the residuals are shown on the vertical axis and the independent variable on the horizontal axis. Residual plots are easy to use and they convey much information quickly. As with simple linear regression, it is an important tool to determine whether the assumptions of the multiple regression model are met. We may plot the residuals against the predicted values of the dependent variable, against each independent variable, against time or order of the selection of the data points, and on a probability scale to check the normality assumption. In Figure 11.11, it is a plot of the residuals produced from the model with two independent variables, M1 and price, shown in Table 11.9, against variable M1. It appears that the residuals are randomly distributed with no pattern and with equal variance as M1 increases. Figure 11.12 is a plot of the regression residuals against the variable price. As we examine this figure carefully, we see that the spread of residuals increases as price increases. Thus, the variance of the residuals is not constant. We have this situation called heteroscedasticity, which is a violation of the assumption of equal error variance. In such cases that the ordinary least squares or OLS estimation method is not efficient, then we use an alternative method called weighted least squares or WLS.
So for the figure 11.13, which is residuals versus time, it is a plot of the regression residuals against the variable time, that is the order of the observation. This variable was not included in the model, and the plot could reveal whether time should have been included as a variable in our regression model. The plot of the residuals against time reveals no pattern as time increases. The residual seems to be more or less randomly distributed about their mean of 0. So moving on for our next figure, which is 11.14, residuals versus predicted y values. This figure is a plot of the regression residuals against the predicted export values y. We leave it as an exercise to the reader to interpret the information in this plot. So that is for the residuals versus predicted y values. Moving on to our standardized residuals. We must remember that under the assumptions of the regression model, the population error are normally distributed with mean 0 and standard deviation. As a result, the errors divided by their standard deviation should follow the normal distribution. So next is the normal probability plot. A normal probability distribution plot is a plot that is used to determine if any numerical data is or has a normal distribution. If the data follows a normal distribution, then a normal probability plot of the theoretical percentiles of the normal distribution on the x-axis versus the observed sample percentiles on the y-axis should be approximately linear. So here in figure 11.15, the deviation do not appear to be significant. Consequently, we assume that the residuals are normally distributed.
At this point, I will be introducing some concepts and their definitions that are relevant in a multiple regression analysis. One of those is an outlier. Now, what is an outlier? An outlier is basically a data point that is separate or far from other set of data points. It is an unusual observation or value from the set of values. In other words, outliers are data points that are numerically distant from the rest of the data set. Now, to determine an outlier, we just simply look at the graphs of plot. The easiest way to detect an outlier is by the graph of the dataset because it contains the plots or the values. The mostly used and favored visualization tools to look for an outlier are the scattered plot and box plot. Figure 1116 is an example of a scatter plot that contains the set values plotted and, importantly, an example of an outlier. Encircled here is an outlier. Now, what does it mean when your graph has an outlier? Does it affect your analysis positively or negatively? Here are the possible effects of having an outlier in your regression model. An outlier may have severe influence on fitted line in a way that it can change the equation of your model. Here is a graph with an outlier, and the other one does not have one. As you can see, the equations are really different given that most of the values are similar. Another thing is that the magnitude of the effect of the regression model depends on the position of the outlier. Outliers in the x direction greatly influence the position of the regression line, and on the other hand, outliers in the y near the y direction barely affected the position of the regression line. However, in some cases, we do not remove an outlier. If there are outliers in the data, they should not be removed or ignored without a good reason. Whatever final model is fit to the data would not be very helpful if it ignores the most exceptional cases. Removing an outlier has its effects too. The correlation coefficient, or as we denote it as R, and the coefficient of determination, or R squared, would increase. The correlation coefficient would get closer to 1. Another thing is that the slope of the last square's regression line would increase. Although we need to remember that the effects also depends on the outlier's position on the y and x axis. Moving on, we will be defining influential observation. Influential observation is a point on a scatter plot that has a large horizontal gap containing no points between it and a vast majority of the other points. Both the outlier and influential observation can affect the regression model. However, in an outlier, as mentioned before, it depends on the position of the outlier. If it is close to the y-axis, then it would barely affect the model. You might get confused between these two, so here are figures and examples that determine an outlier and an influential point. Now, as you can see here, the outlier is the farthest point from the regression line, and the influential observations are points that are far and have large horizontal gaps. So I guess that is all. Thank you for listening.